Good day and welcome back to the third and final part of our discussion on implicit differentiation. And I'd like to take this opportunity just to encourage you to hopefully continue practicing suggested problems from the book. Remember that kind of what we do together in these videos and even what you do in the graded homework just make up a small subset of the problems and really a starting point for your learning process. In order to fully understand the material and do as well in the course as I know you all would like to, we need to be going through suggested problems and not just completing them, but really focusing on understanding what's going on. So let's go ahead and jump into this example. Very typical problem. Once again, we're starting off with some implicitly defined curve, and we're being asked to find dy dx. And the difference in comparison with the previous example is that we're asked to do something different with the derivative once we find it. So let's go ahead and differentiate. So implicit differentiation. Remember, we differentiate both sides with respect to x. There'll be some number of dy dx's involved, and we algebraically isolate. So working our way from left to right, the derivative of x cubed with respect to x is just an explicit derivative, 3x squared. The derivative of y cubed with respect to x, that is an implicit derivative. And when we differentiate that implicitly, we differentiate the y cubed exactly as we would like to. And because it's implicit, we multiply by dy dx. And we also need to take the derivative on the right. And we have a good starting point. So I would like you to pause the video and finish up finding this derivative dy dx. Hopefully at this point you've paused the video, you've gone through a few computations. So on the right, if we continue on, when we differentiate 6y with respect to x, what I want to note is that it's really a product rule. You have one function, 6x, multiplied by a second function, y. So we take the derivative of the first, which would be 6, times the second, plus the first, 6x, times the derivative of the second. And when we differentiate y with respect to x, that's an implicit derivative, and you end up getting back exactly what you might expect, dy dx. And now we're in a standard position. We've differentiated with respect to x. There's some number of terms that involve a dy dx. We are going to algebraically group those terms together on the left and isolate. So on the left, we have a dy dx times 3y squared. And I'm going to also take this 6x dy dx, and I'm going to move it over to the left-hand side. So I'm going to be subtracting away a 6x, and I've already pulled the dy dx out. So I've just kind of combined those two steps together. I've moved this far right term over to the left, and I've pulled out a dy dx. Then any remaining term is going to either stay on the right, or I'm going to move it to the right. And lastly, we now have the quantity we are hoping to find. Dy dx is equal to 6y minus 3x squared divided by 3y squared minus 6x. And I do want to take just a very quick moment and note that this matches up precisely with this procedure we've discussed. Differentiate with respect to x, that's going to introduce some number of dy dx terms. Move all of those terms to the left, any other terms to the right, and algebraically isolate dy dx. Now that we've found it, this is where the nature of the problem is going to change, depending upon what we are asked to do with it. And in this case, in part B, we are asked to find the points on the curve where the tangent line will be horizontal. And this is something we've encountered several times, I think, at this point. The tangent line is horizontal when the derivative is 0. So what we would like to do, and what we're being asked to solve for indirectly, is to solve the equation dy dx equals 0. dy dx above is 6y minus 3x squared over 3y squared minus 6x. And I want to know, where is this equation equal to 0? Solve for the x and the y that would satisfy it. Well, a fraction is equal to 0 precisely when its numerator is 0. So in this case, that would mean 6y is 3x squared, or state it maybe a bit more conveniently, y is equal to 1/2 x squared. And let me be very clear, this is just the starting point. And the common question here, and the difficulty of the problem, is determining, what do we do with this equation? Anytime y is equal to 1/2 x squared, the derivative will be equal to 0. But no, we are only interested in dy dx when we are on this curve. So we need to know, what are the points on our curve where y is equal to 1/2 x squared? So the answer to this question, what do? We substitute into the original equation. And when we substitute this into the original equation, we will hopefully be able to determine the points, or the corresponding points, on our curve. So substituting this into our original equation, which was what? X cubed plus y cubed equals 6xy. We want to replace each and every y with a quantity 1/2 x squared. So x cubed plus 1/2 x squared cubed is equal to 6x times 1/2 x squared. So we took each of the y's that we saw, and we replaced them with a 1/2 x squared. And now this is something we can work with. It only involves a variable x, so we will solve, and those will be the x coordinates of the desired points on our curve. So let's go ahead and solve. Working from left to right, we have x cubed plus, and note that cube distributes over the 1/2 and the x squared. 1/2 cubed is 1/2 cubed. X squared cubed, we multiply those together, is x to the 6. And on the right, 6 times 1/2 is 3. X times x squared is x cubed. And in order to solve for x, it makes sense to, group all of those terms together. So in this case, I'll just go ahead and subtract 3x cubed from both sides. And I'm going to write this as 1/8 x to the 6, and we have 1x cubed minus 3x cubed. So a net minus 2x cubed. And when it comes to solving for roots of a polynomial, which is precisely what we're doing here, where does this 6-degree polynomial equal 0, I always prefer to have whole number coefficients. So to make this simpler, let's multiply everything by 8. So I'm simply taking this entire equation and multiplying by 8. X to the 6 minus 16x cubed equals 0. And now this is much simpler for us to work with. Both terms involve an x cubed, so we factor that out. And what we are left with is an x cubed minus 16. And remember, the only way a product can be equal to 0 is if each of those terms is equal to 0. So we have x equals 0 from the x cubed, and then we have x cubed minus 16 is 0. Okay, so x cubed is 16, which means x is equal to the cube root of 16. And I'll note I have no idea what that number is off the top of my head. I know we can plug it into a calculator and get a decimal approximation, but I'm going to leave it exactly in this form because an exact value is typically preferable to a calculator approximation. And this is going to correspond to 2 points on our curve where the tangent line is going to be horizontal. I'm going to create just a little bit of space, and note that those corresponding 2 points have what? X coordinate 0 and x coordinate cube root of 16. And the question becomes, if we know the x coordinate, how do we find that corresponding y value of the point on our curve? And I want you to take a minute, maybe pause the video and see if you can trace back through our work, hint, and determine what that corresponding y value is. And note, if you trace back through our work, we see that we originally started with y equals 1/2 x squared. And we need to know what are the points on our curve that satisfy that relationship. So we substituted it in, and we found the x coordinates of those points. The y coordinates are going to be determined by that equation, 1/2 x squared. So we need to use that to find the corresponding y coordinates. So if x is 0, y is going to be 1/2 0 squared, which I know is just 0, but I'm going to leave it in this form. And if x is the cube root of 16, y is 1/2 the cube root of 16 quantity squared. And these are the 2 points on our curve where the tangent line will be horizontal. And just to kind of recap a bit, let me know the procedure we went through. We wanted to know where dy dx was equal to 0, and when we solved, we of course got something involving x's and y's. And I say of course because our equation was implicitly defined. So to find those corresponding points on our curve, we had to go back to the original equation. So this is a procedure that is useful to be familiar with. That completes our discussion on implicit differentiation, but we will pick up in our next video talking about related rates by using implicit differentiation to help us solve the problem. So stay tuned and take care.